Let's see. You guys can see my screen, right? So
we can see your screen. Might want to make it full screen. There you go.
okay. So I'm gonna give you a little bit of a top level here, and I'm gonna go in, give you an update what's going on at work, and then we're gonna dig into this fourth processor that I see. Everything that Dr. Ting's working on, you know, could be used on this new processor as well. I'm calling it CISC on RISC Engine, or Core 1. And the reason is you can have, when you build a RISC microprocessor, you're focused on speed of execution of the you know, of the opcode. So that opcode has to meet timing constraints inside the IC. So a code can't go too long. You know, it basically, a code has to complete when the next, you know, CPU cycle goes. With my particular, what way I designed my unit is I have a busy flag, and as long as the core is executing, processing has stopped. So it's going to be a hybrid of combinational logic and you know, and more of a time system. So that's kind of the goal that I have for the system. And let me just give you a quick update on what's going on. Let's see. Why? Let's see. I don't know why I can't just just a kind of an update for those people that don't know what I'm doing. I designed the computer for this new manufacturing robot that's going to be flying in 2023. It's called Archinaut 1. You can see right now we got a 3D printer making this beam, and it's pulling out solar film. So it's going to print. It's a pseudo solar cell. It's just plastic material. It's just a demonstration project that NASA's funded to the tune of 74 million. So we're 3D printing it, and then we're going to use a robot arm and move the 3D printer to the other side, and then print the second one on this side, which was the original concept. And I designed the computer for this system, and I even designed the motor controller. I'm talking about the electronics. So I chose 2 FPGAs, and we have one FPGA that's running the 3D printer that has 14 motors in it, and each pulse width modulation channel is running at 25 kilohertz, which is really fast for PWM. So I have a special circuit that uses an NPN and a P channel discrete transistors driving the gate, because the gate has high capacitance. You can't drive it, can't turn a FET on and off that fast with just a pull-up resistor. So anyway, that's what I'm doing at work. Let's see. So oh, there it goes. Now it's working. Okay, so as you know, I originally was working for a company called Made in Space out there in Silicon Valley. This company called Redwire Space got some serious deep pockets. Some outfit called Industrial Partners, who go to pension funds and say, Mr. Pension Fund, would you like to invest 5% of your pension in new startups, you know, to make more return, and we'll manage that for you. So Redwire went out and bought basically Main and Space and Redwire merged, and Redwire then went out and bought 8 other space companies: Adcol Space, Deep Space Systems, uh, a whole litany of these smaller companies. When I started, I was the 44th employee, and after Redwire, what their current size is 500 employees. So we finished the Archinaut 1 NASA CDR about 2 weeks ago. NASA was very pleased. When we were at PDR, NASA said, we're skeptical we could even design a computer. And we proved them wrong, and they were very happy we did. They said they were really impressed with because we have the computer 3D printing as we speak. So so Archinaut 1 project is basically done. I'm doing some cable drawings and stuff and some last minute things. And I have been, I'm one of the founding employees of a new AI robotics group. They're calling it Mechatronics and Intelligence Group. Some business guy came up with that, whatever. Anyway, and we're gonna, so based on what we developed with Archinaut 1 and the Archinaut avionics, we're gonna start building artificial intelligence on top of this. The guy that is the lead of our group, Kevin French, has a PhD in robotics, and he's done a lot of work with vision-based robotics. So he's going to work on the vision robotic stuff. I'm going to work on the lower level stuff, like collision avoidance and the controlling system using FPGAs and that sort of thing. I do have them. I planted a seed about Fourth. I have not sold them on the idea yet. I got to show them something that'll knock their socks off. So, so anyway, we're going to be working on space assembly robots. So you think of, 100 robots in space, all working collaboratively to build a large space structure. That's the kind of thing that Archinaut 1 is a stepping stone to, and that's what we're going to be working on. It's a technology for that. So I'm going to be doing this full time. We also want to have planetary rovers for doing mining. And gee, who do you know that's a gold miner? So also satellite repair. So this is the idea: a fourth FPGA computer kind of block diagram. So let's talk about the GA144 for a minute. I love the idea of massive fourth, parallel computers. But when Chuck decided to go down this path, he had to fix the size of how big it is. They're 8 bits wide. They can access a limited amount of memory, each one, but they all have dedicated memory. How do you get data across the chip? With the GA144, you might have a fourth computer on an input pin and one on an output pin. And then how do you get the data across the chip? And you wind up tying up some of these internal fourth computers that are just kind of moving data around. At least that's my perception. If somebody knows different, please correct me, but that was some of my thoughts on it. And I was thinking, why not just use an FPGA, and then you can architect whatever system you want. So Dr. Ting has done this a couple decades ago, maybe 3. He did a VHDL version. And the other thing about this computer is I wanted to use System Verilog. So System Verilog is very high level. It's like C. It's pretty much C syntax. You can have structures in it. You can have a lot of high level stuff in it, and you let the synthesis tools build the hardware in the fabric. If you do it the way that Dr. Ting did it, and the J1, and then way Ilya did it, who's in our group. He's done it. He's also done it in He's done it in Verilog. The other two are in RTL Verilog. The thing is, you're kind of designing at a very low level, you know, bit to bit and register to register, that sort of thing. It's pretty low level. A lot of details. You got to make sure everything works. If we use system Verilog, then we can do some pretty interesting things at a much higher level. That's what kind of got me going down this road. I designed it in VHDL. It wasn't finished. It didn't work, but I conceptually designed it in code back in the late 90s when I took an AI class. So moving forward, Dimitri, who is one of the guys in the fourth 2020 group, he's out in England, and he does verification for a living. So he knows system Verilog in and out. That's all he does all day. He took my VHDL source code and he converted it into system Verilog. So the idea is like what we see here. So we have a main fourth computer, and this would be, you communicate with, if it's on a robot, you communicate with the user, using the fourth computer. Now you'd also could have a stripped down version where you just want a very basic fourth engine, fourth microprocessor doing something. So you can instantiate, is what it's called in FPGAs, instantiate as many processors as you need. It will probably wind up to be like 3 pages of source code or so to build a fourth processor. So this is kind of an example how you could distribute these fourth processors around, and it's kind of conceptually similar to the GA144, but because these are 32-bit wide, and they do each one of these processors uses internal RAM that's inside the FPGA. When I write embedded systems in fourth, I hardly use any RAM. So this is super fast SRAM that will be tied to each one of these fourth computers. Will have its own SRAM. It'll have its own flash memory, ROM memory. The other, so that's the basics of it right there. So very high level system Verilog code is very easy to read and understand. Let the synthesizer build the circuit. Most FPGA force are coded in RTL. Design a stripped down fourth microprocessor for multi-processor applications. So we'll take what I developed with this fourth computer and strip it down to a very basic processor. Maybe we'll only implement a subset of fourth code. I notice when I write embedded system code, I don't think I use more than 20 fourth words. The code will be super fast, and each one will be a dedicated process in system Verilog. So think system Verilog as the assembler for this computer, and then fourth is the high level processor, high level code. So I gave a presentation, I don't know, a year ago about kind of getting down these lines, and I was thinking of building a tablet using this system. So you would use like the ESP32 for just doing Bluetooth and ADC and stuff like that, since they're so cheap. I'd have a dedicated RAM. I've done this before at a previous job. So I'd have Verilog code that's running the display. The display would have its own memory, and then you'd also have non-volatile SRAM as the system memory for the fourth code. Then there's also, of course, an SD card. So this is a basic computer, 0 operating system. Fourth is the operating system. So this is what we're doing at work. We got a RISC-V core inside. That RISC-V takes 10,000 lookup tables to implement. It's supposed to be reduced instruction set. Takes 10,000. It takes a huge amount of the fabric just to implement the RISC, so that our software group, can use standard C compiler to write the code and that sort of thing. Because we're using the von Neumann approach, there has to be a bus, and so all of our different peripherals are hanging on this bus, and the RISC-V is basically reading and writing to memory mapped registers on the bus to get to these parallel processing, Verilog written engines to control things. Like the motor controller at the top there, it's driving 14 motors simultaneously at 25 kilohertz PWM, pulse width modulation. We're running an end effector. We have heaters on the spacecraft because we have to heat up the electronics to keep them in the heat range for operation. BCT network controller, that's talking to the spacecraft itself. And we have 32 bits of SRAM, and it is only 512 K by 32 bits. But it turned out I made that choice, and it turned out I was a little bit nervous about it because we could run out of RAM. But SRAM runs 4 to 5 times faster than DDR. So I wanted to use SRAM, and it was a simpler interface as well without all the control operations and everything else, control lines for DDR. And it turned out it worked. They were able to do all the coding and have RAM to spare. And we also have a 2 gig 8-bit flash for storing code and storing the directions on how to print the beam and that sort of thing. So let's see. So, I want to be able to put the Triune architecture on here as well as the Dr. Ting's fourth. So I'll make sure that all the fourth words comply with Dr. Ting's fourth words. Dimitri has already written Prolog in fourth, and you can actually create with this system, you can create complex opcodes that take a long time to execute. In other words, a long time, I mean, instead of an let's say the opcodes have to run on a 50 megahertz system. The clock would be 50 megahertz or 100 megahertz, but an instruction can go way longer. Maybe the instruction, you could only do 10,000 of those instructions per second, right? So that means that I have a busy flag that is set when the decoding engine executes for the opcodes, and it is blocked until that busy flag is reset to 0. So we can do things like we can microcode other languages inside the system. So Prolog, we have a ROM inside the boot ROM. I call it boot ROM, but it's just basic ROM. We could define words. In other words, we could take the source code that Dimitri has written for Prolog, and we can define those in the ROM memory, and we can call that ROM memory, right? So it's just like you have a basic for system, and you create this new language on top of it, and you can execute your new words, right? So you can put words that you want to have compiled basically inside of this this engine, and put it in ROM and call it and create an opcode to call that. So now you've just extended the engine to include very complex instructions. I wrote a neural network language in Forth back in the 90s. It was very easy to write, and so that could be also implemented in this engine, or a probability engine. Anything you can think of, you could implement it, and then you could write it in microcode in the ROM. And now you not only have Forth, but you've created a whole new AI language, very high level. That's all inside this FPGA. You know, we can do voice recognition, vision. We can have vision routines that become these complex opcodes. And of course, most of you have seen this already. This is my Triune OS that emulates the way that we work for real-time intelligent robot control. And it's probably several pages. The core engine of this is several pages of Forth. It's not hard to implement. So this would also be implemented in the main processor. The other sub-processors that are executing subsystems don't need this. They're just sitting off to the side as parallel machines inside the chip. So I've kind of gone over this stuff before, the 3 levels and how they work. So, oh, this is a slide from from work. So I was kind of promoting maybe we could do this at work, but I haven't got there yet. I got people are interested, but they haven't bought into the idea of using Forth yet. Okay. But I'm in a position where I think we can get it in the system, because I think it should be Forth should be on the wireless deep space command link that's very low speed, to allow us to use Forth interactively to debug the spacecraft, you know, to add new commands to it, i.e. words and that sort of thing. I think that's just it. Forth is a natural for that. I'm going to try to get it involved there. So that is, if I can pause share. Okay, I'm not sharing my screen now, right? Did I stop sharing?
No, your screen is still there.
Oh, stop share. There it is. The little red box. So, yeah, so I wanted to show you the code. Let's see. All right, so this is called Libero. It's Microsemi, or Microchip actually bought it. Oh, I got to share my screen again. Hang on. Let's see. Now, where'd you guys go? Okay, let's see. Share screen. Okay, you see my screen now?
Yeah, we see your desktop.
Okay, so here's the source code. I just want to kind of go over the source code with you guys. So we're using typedef and enum to create the names. You know, that will obviously, enum will make it into a unique number. So these are the names of the opcodes here. So I tried to you know, break them out. These are stack operators. These are memory operators. And I'm thinking of not implementing all these, like just have a 32-bit store and fetch. Cut down the cut down the number of opcodes instead of implementing everything. But I did put a lot of opcodes in here that I think I'll be taking out some of them. But this is how you design it. So these are, you know, the different loops you can do. So just defining the names of the opcodes, and then so we have a type depth here structure packed, and so we basically, you know, this is the opcode structure. So basically we have that inside here, and then and maybe Dr. Ting and Brad and some of you other guys can talk to me about this. I was thinking of having an immediate flag on this opcode structure. So when the interpreter you know, parses the opcode, if the immediate flag is set, it will say during compilation, then it would execute rather than compile. So if you guys have any thoughts on that, speak up. It was just an idea that I had. Okay, so these are a parameter list. So you put the address size of the fourth engine, how large, how wide the data size is, how much memory you want to give it. So basically you change these numbers at the top, and the synthesizer will create, you could create a 16-bit fourth if you wanted, a 32, a 64. It's how you define it up here. I'm defining how much boot ROM it is, and how much you know, on chip FPGA RAM is used. So you'd probably want to keep this as small as possible for each one of these processors. Right now I'll just make it big because I just want to get one working. This is the old way. So this is the old way of defining things instead of using enum. Okay, so now you define the inputs and the outputs of your machine, and let's go over here for a second. So this block diagram is here's the fourth engine. You see the inputs and the outputs on this block. That's what we're looking at. This defines those. So you can see coming down here, I'm using the RISC-V board for this development. And so when you see these outputs and these inputs, they're over here on this block diagram. You can see them right there. So this is what you do. You create this this logical, you know, block that does something, and you can duplicate it. So I could put, you know, 4 or 5 of these fourth processors together and come up with maybe a bus or something for them to talk to each other. I probably would do a serial interface, because processors don't need to communicate with each other that fast in most applications if you factor the application well. So let's go back to the source code. Okay, so that's now these logic statements. You notice on regular Verilog, use a reg, you know, for a register. Logic is a new way of saying it for system Verilog, and it gives the synthesizer more ways, more room to implement what you want. So we can do some more magic than if you define them as reg. So it's a system Verilog thing. This is something that Dimitri did. So this is how I was talking with Dr. Ting about this project. He said you should use the circular stacks. So this implements the circular stacks. Dimitri wrote this code and tested it. It works. So we can have, and you notice I have data size. So remember at the top, we defined how big the data size is. So if you want a 16-bit fourth processor, that would be 15. If you wanted 32-bit wide, it would be 31. So you can make those changes in the parameters at the top and control what you're building. So
Sorry to interrupt, Don.
Sure.
Can you wrap it up in about 5 minutes? Is that within the realm of the possible?
yeah, or people can drop off and we can continue talking.
No, we've got 2 other talks after you.
Oh, I didn't know that. I thought I was
Okay,
last.
well, the agenda was sent to the list and it's on Meetup.
You got it.
Now you know.
All right.
Sorry
5
to
minutes it
interrupt
is.
you, but thank you.
No worries. 5 minutes it is. So, we have here, right? We just make here a register, for example. Base is a register. There's a state register. So we're just defining the logic of this machine. Here's an example of a task. So a task in System Verilog is just like a function. So what this is doing is this is some test code. So I'm loading, the first cell of the ROM with 10 and the second with 55, and then I want to add the two together, and then I'll have an opcode called inboot. That means you're gonna, and you could put an opcode display, right? So which is dot. So that's how you could microcode things like Prolog using this kind of technique, and you could have basically colon, semicolon, implemented in there. And so you can create these tasks, automatic tasks, and you can do things in there at a very high level. So this is an example of actually implementing the opcodes. Notice there's a busy flag. So I set the busy flag to true when this is executed, and it's a big case statement. So for the abort, I'm going to do a reset. I'm going to set busy flag to false. So that as long as the busy flag is true, this cannot execute. It's blocked. So you could have code that's very long. So here's times. We just take the the pointer to the 2 items on the stack there, and we multiply them together, and then we move the circular data stack pointer, and then we set busy to false. So that's pretty much what I wanted to go over. And then at the bottom, this is not done yet, but you have an always statement. So you're going to have, this is going to be something like what the inner interpreter is going to be down here. This is not runnable code at this point in time. So I guess we'll open for questions. No questions?
Hey, Don. If I recall from fourth meetings way long ago, that there was fourth used on a satellite, like sometime in the past, that they were able to upload code changes to it.
NASA and fourth, there's a lot of fourth that was used all over a lot of the different missions. If you go to Fourth Inc.'s page, space applications, it lists a lot. NASA Goddard, there's some guys, they built a massive parallel processor back in the 80s using fourth. It's just amazing how much fourth is out there in space already right now, but you just don't hear about it. But yes, your answer is the answer is correct. I would like to use it for that at work. Any other questions?
Some of it was from the RTX 2000 series parts that were space ready. That was it's hard to find space ready anything, and Harris, I guess it was, made those.
Right.
Don, is there a book or a reference you would recommend for learning Verilog and working with FPGAs?
Yes, there's one if you do a search for System Verilog Sutherland 20 System Verilog 2017 Sutherland.
Okay,
It's kind of expensive, but it's worth every penny. If you read that book, you'll know all the high level syntax, and it'll blow you away what you can do, because you can build very complex systems in very little code in a very high level abstract way. And this is brand new, 2017, when they really got System Verilog fine-tuned and working sweet.
okay. Sutherland System Verilog 2017. Okay, I'll
That'll get you
take
there.
a look at it. Thank you.
Mm-hmm.
Well, thank
Okay,
you very
this-
much, Don.
You bet.
Thank you very much, Don. We appreciate it. Sorry about the disconnect. Going forward, I'd like to remind folks that our Zoom meetings are hopefully consisting of 20-minute max presentations, and we're not strictly enforcing that until fourth day. But if you have a longer presentation, I recommend you consider making a YouTube video of your own, and then you can hopefully give us like an overview or an intro and a link to your longer presentation. We're pleased to accommodate and host any of those things that we care to come across. Brad isn't either following this rule, but he's up next. And since he's paying attention, I'm sure he's ready to go. So Brad is talking about deep learning in fourth, and this is going to be part one.
And I will try to keep it a little terse.